Hello fam, this is Dr. Shozi and we are on tutorial 2, Learning Opportunity 2. The first problem that we are going to look at is as follows. Let f be differentiable at a point z0 in the set of complex numbers. Show that f is also continuous at z0. So here we are required to prove that if f is differentiable at z0, then it is also continuous at z0. So that's what we are required to prove, and we are given an assumption to start with. So let's start with our proof here. So for our solution, is what we are given. We are going to assume that f is differentiable at z0. Let f be differentiable at z0 in the set of complex numbers. So what it means to be differentiable at z0, then if f is differentiable at z0, then the following equation holds. The following equation holds. What is the equation? If f is differentiable at z0, then the equation, the limit at z approaches z0 of f at z minus f at z0 all over z minus z0 is equal to f prime z0 holds. This equation holds. So let me mark this equation by equation 1. I'm going to mark this equation by equation 1. Now, what we want to prove here, we want to prove, or we want to show that when we take a limit as z approaches z0 of f at z is exactly equal to the value of f at the point z0. Then if we can prove this, then it's guaranteed that f is continuous at a point z0. So now let's start. Thus, we can imitate trying to prove this. Let's start trying to find the limit as z approaches z0 of f at z minus f at z0, this difference over here. Let's try doing this. With this, what I'm going to do, I'm going to divide by z minus z0 and then multiply by z minus z0 so that that quantity will cancel itself and the equation will remain the same. So I will have the limit as z approaches z0 of f at z minus f at z0 all over z minus z0. Then I'm going to multiply again by z minus z0 so that the quantity on the denominator will cancel that quantity. Then the standard of the equation is not tampered with. So this is the same as the limit as z approaches z0 of f at z minus f at z0 all over z minus z0 times the limit as z approaches z0 of z minus z0. Z minus z0. That's the property of a limit. The limit of a product is the same as the product of the limits. So now, you can see that we know that the limit as z approaches z0 of z minus z naught is exactly equal to 0. And by equation 1, we have that the limit as z approaches z naught of f at z minus f at z naught all over z minus z naught, that's exactly equal to f prime z naught. So we have that. And therefore, what we have now, we have the limit as z approaches z naught of this difference, which is f at z minus f at z naught, being equal to f prime z naught instead of that limit there by equation 1, instead of this, let me highlight it, instead of this quantity. Now, this quantity is the same as f prime z naught, and this quantity will be the same as 0. So it will be f prime z naught multiplied by 0. So the whole thing will become 0. So this means that I can remove with the limit. So I have the limit as z approaches z naught of f prime z, because the limit of a difference is the same as the difference of limits, minus the limit as z approaches z naught of f at z naught, that is equal to 0. However, the left hand side, you will have the limit as z approaches z naught of f prime z minus the limit as z approaches z naught of f at z naught. That's just the same as f at z naught. That is equal to 0. And therefore, you have shown that the limit as z approaches z naught of f at z is equal to the limit, is equal to the quantity f at z naught. So the function is continuous. The function is continuous at z naught. So we have proved that the function is continuous at z naught. So this is what we are required to prove. Thank you. So we are going to meet again on the next video.